Okay, Regents students, welcome to our first physics video. It's actually my first physics video because I've been doing some stuff with the AP classes, but mostly just review problems. So they started a little earlier, but here we are. This is my first time making a video lesson, so hopefully it'll go well, but there's a few things that are a shortcoming because unfortunately, all the equipment, the demos that I would be showing you at the school, which are unavailable, so we're going to be limited here, but we'll do our best. So you have here the notes. You can jot these down before or after the video presentation, or maybe even during if that's what you prefer, but maybe it's best to do it not while you're listening, because then you could concentrate on basically what I'm saying. I'm going to also include a PDF version of this, so you don't have to look at this video to copy. It'll just be a PDF file. So we're starting with this little short topic, magnetism. You already have the outline for that, but I will attach a PDF version of that in case you left that at school. So magnetism, the Regents has a very trivial treatment of this topic. So we're just going to spend 3 days on it, maybe even 2 if I decide to cut one off so we could start moving with waves next week. So here at the beginning, we have the most basic idea about magnets, the basic thing. If you take a couple bar magnets, first of all, bar magnet has 2 ends. One end is a north pole, one end is a south pole. Those are just words that people used for these 2 opposite poles. So every magnet has 2 opposite poles. I bring 2 magnets next to each other, and you see that the north sides, the 2 north ends, are near each other. In that case, you would experience a repulsion. These magnets would be pushing each other apart. If we bring 2 south poles together, we also get a repulsion. But if we bring a north next to a south, we get an attraction. So it's kind of like charge. Opposite poles attract each other. Like poles, north, north, south, south, those will repel each other. Okay, so the source of magnetism is actually the electrons. They orbit the atoms, and that creates a magnetic effect. Technically, it's called magnetic moment, but you don't need to know that. Also, the electrons have what's called a spin to them. That's also like an orbit, but then like a rotation, like imagine the Earth spinning on its axis. That also creates a magnetic effect. So it's down to the electron level. The electron orbit causes magnetic field B, that's the symbol used for a magnetic field, to point into the paper. Now here's a difficult thing. How do you draw an arrow that goes into the paper? Obviously we can't take our pencil and trace in the air. So what we do is we draw a circle with an X in it, and that represents like what you would see if an arrow were flying directly away from your eye. You would see the feathers of the arrow on the back of the arrow. If the magnetic field comes out of the paper, we draw a dot with a circle with a dot in it. That would be what you would see if the arrow was instead pointed directly at your eye. You would see the shaft of the arrow and then the tip of the arrow. So this is an arrow that comes straight at your eye, and this is one that goes straight away from your eye. So this would create a magnetic field into the paper. You don't need to know that. That's more than you need to know. Just that the electrons create magnetic field. So for most matter, these represent the magnetic fields of all the individual atoms. You see here that it's basically all random. So each atom's B, or magnetic field, orientation is random. The net effect is that all of the B's cancel each other. But when you take iron and you put it in a strong magnetic field, it can become permanently magnetized. So what we have is you see all these atoms. They're not perfectly aligned, but more or less they all point toward the right. So that creates a magnetic field. The atoms' magnetic fields are permanently aligned, but dropping or heating the bar can destroy the alignment. So you could take this bar magnet and literally throw it into the ground, bing, and the atoms become disaligned from the shock. Or you could heat it with like a blowtorch or something like that, or over fire. Then the thermal effects make the atoms become random again. This end will be the north end, this will be the south end. So if you diagram the magnetic field lines, this is kind of like analogous to the plus, and this the minus when we drew electric field line diagrams. The magnetic field lines come out of the north and into the south. Okay, so you see they curve around and come back into the south, except for that one. This one also curves all the way up here and comes back into the south eventually, but it goes off our paper, so we just draw it stopping here, but it really doesn't stop, and then continuing up over here. Here are the rules for drawing magnetic field line diagrams. For any object, they always come out of the north and go into the south. Rule 2, there's an equal number of lines out of north as into south. So you can never have just the North Pole all by itself or South Pole all by itself. You've got to have, if you look back over here, 7 lines coming out of the north. Every single magnetic object would then, with 7 lines coming out, has to have 7 going in over here. You can never have a magnet with one pole stronger than the other, or just one pole all by itself. And you might be saying, well, if here's a permanent magnet, right, if this were made of metal, why don't I just cut it in half? And now I have a North Pole and a South Pole. What would happen, because this comes from the atomic alignment, if you split this here, these would become the South Pole. So you'd actually get 2 magnets like this. One with a north-south like that, and a north-south like, so you wouldn't get 2 magnets, each their own separate pole. You would still have 2 poles in the pieces. Okay, so, and then also the lines never cross, and there are no gaps at the magnets. So you see here, the lines start right at the magnet and go all the way into the magnet. And careful here that they don't touch each other, because a lot of times students will draw the next line coming off right from the same point. Lines can never cross. You can also have a horseshoe magnet, which would just be a bar magnet bent into a horseshoe, okay? And then you have a north and a south pole. The magnetic field lines go across in between, and then they curve around like that. So it's just a distorted bar magnet. Notice again, I have 1, 2, 3, 4, 5, 6 lines coming out of north. How many do I have going to south? 1, 2, 3, 4, 5, 6 lines going into south. So note that none of the rules 1 through 3 violated. 6 lines out of north, 6 into south, etc. Sometimes you can have pairs of magnets. So here we have a magnet like this with a north and south pole facing each other. The field lines coming out of the north this time don't curve into south, but they curve into the south here, not this south pole. So you see the lines going in and then coming out this end. Technically these lines, some of them would curve all the way around to this south pole over here. Now, I purposely made a mistake in this diagram. Take a minute to see if you could figure it out, okay? And maybe you could pause the video, because I won't pause, that'll just be annoying. But pause and think about it. Okay, so what is the mistake? Notice here, 5 lines coming out here, 5 going in here. Good, this magnet has equal lines going in and out. Here, 5 lines coming out of this bar magnet. Oops, only 3 going in here. So I'm missing 2 field lines. So I got to put them, got to be real careful. I made it a little tight here. So if this were like a quiz, I'd probably erase all these and make them a little further apart so I wouldn't lose any credit. Someone might say, oh, those are touching. They're not supposed to be. Okay, so 5 field lines, 5, 5, 5. This can have only 5 lines here, and then maybe this magnet only makes 3 out of this end. That's okay, because this magnet might be weaker. But if 3 lines come out of this side, then you better only have 3 going in here, okay? Okay, this is a diagram for when 2 north poles face each other. The field lines can't cross, so they sort of, you could think of them as repelling each other. But really, they curve away from each other so that they don't cross. But they come out of the 2 norths. Again, 6 lines here, 6 there, 6 here, 6 there, no crossing. Same thing here. I have 2 souths, so it's like this one, but the field lines have to come in over here. So I've got 4 field lines, 4 field lines. Good. 4 field lines, 4 field lines. Into south, out of north, no crossing. Okay, the next thing. You can use a compass, which is nothing more than a small magnet that's free to rotate. And you could use that to detect a magnetic field. So in my house here, going this way is to the, let me think for a second. Yeah, that's to the north. No, sorry, that way's to the north. So north goes this way in my house. If I took a bar magnet and I put it on a pivot like this, in other words, I put a little pin and I let it balance on there, the magnet would turn like this. If I turn it again like this, it would turn back. I turn it this way, it turns back. So humans discovered this hundreds of years ago, before they even knew what magnetism was. And because this end of the magnet pointed north, they said, oh, let's call this the north side of the magnet because it points north, and this the south because it points south. So that's where the terms came from, because the magnets were used in geography and navigation. You can use a compass to detect magnetic field around a bar magnet or any magnet. If you put little compasses around this bar magnet, I drew the field line diagram, approximate, you would find that this little compass would always swivel to align itself with the magnetic field at that point. So here the magnetic field's going like this, so the little compass would go and line up like that. Over here, it would go and line up like that right there. And so on and so forth. So often on a quiz, Regents, you draw these little arrows to indicate which way the little compasses would go at those particular locations. So again, we called this north because it pointed north. But here's a bit of a problem, what it did. So I'm going to turn the page here. If this is pointing that way to the Earth, then the Earth itself is a giant magnet. And this part that's pointing to the north must be attracted to the opposite pole at that part of the Earth. So what's facing to the north is actually the opposite pole of this. When humans decided to call this north, that meant that the Earth's north pole in Canada, above Canada, is actually magnetically now the south pole. So the north geographic pole is the magnetic south pole, because bar magnets, the north side attracts to the top of the Earth, meaning that that's actually going to have to now be the south pole. So when the humans hundreds of years ago called these bar magnets, called that north-south, they actually made it so now we have to call the north pole of the Earth the magnetic south pole. So the field lines come out of Antarctica, and it's not exactly at the north and south pole. It's a little bit off where the poles, the magnetic poles are. The Earth rotates through an axis like this. The magnet poles are a little bit off of that. So the Earth has magnetic field. You have to be able to sketch. So you imagine this is like a circular bar magnet or spherical bar magnet, where we have one, oops, I made a mistake here. Looks like a little mark. But we have 1, 2, 3, 4, 5, 6, 7 lines coming out of the bottom of the Earth, Antarctica. So we've got to have 7 lines going into the part, above Canada, the northern part, which is actually the South Pole. So that's our first lesson, Magnetism 1. Basic concepts, and just jot them down and answer the questions. And then when you have questions on the questions, I'll actually put the PowerPoint answers up with the assignments. So as you're doing the homework, you could see the answers. Then there'll be a sheet, the Google sheet, where I'm going to ask you to make marks for anything you don't understand. Then I will make a little, maybe a video or a sheet of paper explaining any questions you'd like. Say you have a question on number 3. You indicate, I don't know how to answer question 3. And then I'll make a separate little thing to answer your questions. And that way, hopefully, we overcome this obstacle of communicating through the internet. Okay, so hope it went well, and just be patient for the next video.